So this question asks us to find the major resonance contributor, and this is what you're set up with. Well, the first thing we can notice is that the carbon is on a -1 formal charge. So what does this mean? Well, we know that the 4 is the valence electrons. We don't know what the variable x is, and we know that the answer is going to be -1. So we can go ahead and minus the 4, and then divide it by negative. You got x is equal to 5. So it's got a total of 5 um, bonds or dots, a 1, 2, 3, 4, 5, as we can see. So what do we need to do? Well, if we were to get rid of one of these pairs of dots and turn it into a bond, well, now we would solve that issue and it would no longer have that formal charge. So let's go ahead and do that. That's how I would attack this problem. So now that I've moved this over, this seems like a great plan. But now the issue is this carbon right here has more than an octet. It's got 2, 4, 6, 8, and we just added another one, a double bond, which will make it 10. So that does not seem like a good idea. So what we need to do in this situation, what I can start doing is looking upwards. What can I do with this oxygen, with this pi bond? Remember we said you can only move the lone pairs of electrons and you can only move the pi bonds. So we can't break these single bonds. We can't really do anything with those. But what we could do is grab one of these bonds on oxygen and move it over to a lone pair. So what does that create? That creates a lone pair of oxygen with, here I'm going to draw a line down the middle, with just a single bond going to this carbon. And then you've got that, you got a double bond. You've got the hydrogen up here. And then you've got hydrogen here, hydrogen here. Okay. So now you've got this carbon with a 2, 4, 6, 8. It fills the octet. This carbon with a 2, 4, 6, 8. It fills the octet. Now hold on. Our total charge for this molecule was a -1. So we also have to recognize that this would also need to have a -1. So where is the -1 charge? Well, let me check each one. It's definitely not on the hydrogens because they all only have one bond. The carbon has 4 lines and has 4 valence electrons, so it can't be that. 1, 2, 3, 4. 1, 2, 3, 4. So let me check out the oxygen. Well, the oxygen needs to have 6 valence electrons, right? It's got one line, and it's also got 2, 4, 6 electrons in the lone pairs. So how much have we got? We got a -1 formal charge. So now the negative formal charge is going to go to this. Now your next question may be, why is this the major contributor? What makes this the major contributor? Well, if we look at our rules, the number one rule is obviously to have as many octets as possible. Okay, well, we filled in that rule, but it would have looked the same whether or not we were in this one or this one. Either way, we had the same number of octets. So that definitely wasn't the difference. The next one is to have as many bonds as possible. And once again, we haven't really changed much. We have the same number of bonds that we did before because we moved this out to a lone pair and we started out with this lone pair down here. So once again, no difference made right there. The third and final way, there's actually one other way that's depends on separation, but that's not a thing that we've got going on here, which is pretty much it says that we need to have as little formal charge as possible. But once again, the formal charge is going to be the same, and it's not like we have 2 negatives and a plus, so either way, it's not that. So why is it that this oxygen has this negative charge as the major contributor rather than this carbon having the negative as the major contributor? Well, it's based on the electronegativity differences. The electronegativity of oxygen is actually higher. It's more electronegative than carbons. So what does that mean? That means we want the more negative charge towards oxygen. So in this case, that is why this one is the major contributor, and that's how you find out how to build that resonance structure.